So now let's talk briefly about Hartley's law. And just so you know that Nyquist, Hartley, and Shannon were all roughly around the same time, and they were working on communication limitations of the telegraph. So the idea of pulses was very much near and dear to their heart. And what Hartley said is, well, let me extend Nyquist's maximum pulse rate for a given B. And what he did that's different is he said, let me take into account the resolution of the receiver. So in Nyquist's theory, I could make M go to infinity and I'd have no problem. But if we have a fixed supply voltage, then as M increases, the unit between each level is going to get smaller and smaller and smaller. And as you can imagine, that's going to create a problem for receiving. Because the receiver can only detect incoming signals within delta V of a threshold, and that makes sense. Let's say each threshold was 50 millivolts. We probably could receive a signal that's maybe plus or minus 10, 20 millivolts within that threshold. And this redefines the total number of possible levels because of this resolution limitation. And so Hartley just redefined H as 1 plus A over delta V, where A is our maximum signal voltage and delta V is our ability to detect. And so a great example of this is if you have an ADC, it is going to take its reference voltage and it's going to define it by the number of steps. And this is going to be the reference voltage divided by 2 to how many bits of an ADC it is. And that's going to give you the LSB. And typically, we need the LSB to be twice of V, of delta V. And the reason for that is, if you think about it, you may have a step that moves up here, and here's another step, and basically I can detect anything in between this. And so if I want to maximize or minimize my height, this needs to be twice what this distance is. And so now we can define our rate simply as Fp, the rate at which we can send pulses, times log 2 of m, and all we do is plug in the 2b, which is from Nyquist's theory, and now we can plug in Hartley's modified m, which takes into account the limited resolution of our receiver. So let's look at a couple examples of the Nyquist-Hartley. So let's say we need to send 256 kilobits of data with a bandwidth of 20 kilohertz in a noiseless channel. How many levels do we need? So we've got 256 kilobits per second. That's our capacity that we need. And so 2 times 20 kilohertz log 2 of m. And so all I need to do is get out my trusty calculator, and I can see right away 256 divided by 40 is going to be 6.4 equals log 2 of m. And so this just tells us that 2 to the 6.4, sorry about that, 6.4 equals m. And if I take 2 to the 6.4, I end up with equals 84. And I'd have to round that up to 7 bits if I wanted to build that. So 2 to the 7 is 128. So I'd round this up so that m is equal to 128 levels. Okay? And that would allow us to supply 256 kilobits per data and a 20 kilohertz bandwidth. Now let's assume that our ADC can detect each level at plus and minus delta V, as I said before. And let's assume delta V is a half a millivolt. So what's the lowest ADC reference voltage that we can use? And so what we're going to do is we're going to say we've got m levels, right? And we know that m levels, and each level needs to be equal to twice delta V, right? That's where we had the statement in the previous slide where we said that we can detect a threshold that's plus or minus a delta V, and this height is 2 delta V. And so we're just going to take 128 times 1 millivolts, and we end up with 128 millivolts is our reference voltage that the ADC can use. It's the minimum. We could actually use a much higher one. That's just the minimum that we would use. Okay, so we can see how resolution fits into our choice of M and our receiver. If we only had a 100 millivolt supply, for instance, we couldn't resolve all 128 bits, that are all 128 levels that we needed to in the 7 bits.